I am recording now, and I'm going to start explaining this first part of the assignment. You have to use this tool. I'll upload this tool today, and we have to evaluate yearly heating and cooling loads and the PV production. So let's do it. If we open this, we have already used the first part of the Excel file, and most of you have included this graphic. And this graphic either for here I have to change this. This is heating and cooling, okay? Because we are using this graphic for heating and cooling. In cooling, we have this option. It goes downwards because the outdoor temperature is higher than the indoor temperature. In winter, is the other way around. It goes upwards, okay? So these are the peak thermal loads, heating or cooling thermal loads. Peak means that we are using the minimum temperature in winter or the maximum temperature in summer. So our systems, the heating and cooling systems, they will have a peak value. So this is the value that we use to dimension our systems. So we go to the systems provider and we let them know, okay, so this is our peak heating and cooling loads. And then they recommend, okay, so for this peak load, you can use this boiler, or you can use that, or oh, this is huge, so there is not a device to provide you with this peak load. You need two devices, this one and that one. Okay, so we can have a conversation with the systems providers for heating and cooling. But now we need to evaluate the energy performance of the building throughout the year. And we don't use the minimum or the maximum temperature. We just use the average temperature. Okay, so I showed you, I think, last, yeah. So I showed you on Monday, we work with this website. It's by default, well, it's in Manchester, New Hampshire, but you can change it, the location. And I showed you that we have to start analyzing different months. View. Okay, so we analyzed the minimum temperature. In this case, is 1 Fahrenheit. But look at this. This is the minimum temperature, and the maximum temperature is 56. So it doesn't mean that our house is consuming the energy, the peak energy that we are calculating when the outdoor temperature is 1 Fahrenheit. Okay, so that's why we need the average temperature. Some of the days will consume more, and other days will consume less, depending on the outdoor temperature. But if we use this average temperature, we have a feeling of what we need. Okay, so the average temperature in January, it's 25. So we can type here 25. Then February, the average temperature is around 28. In March, the average temperature is 35. And that is useful because looking at the average temperature, we can find out if we are going to need heating or cooling. Okay, so if the average temperature is below comfort, and 25, comfort is around 70. So if it's below comfort, that means that I'm going to use a heating system. If it's above comfort, the average temperature, we're going to use a cooling system. So that makes sense because in New Hampshire, it's cold, and most of the year, the average temperature is below comfort, so we have to use a heating system. So this is March, April. In April, it's 48. In May, it's 56. Okay, so even May, um, we need heating. Okay, there might be days in May in which we are above. Yeah, so we have 85 maximum, 86 maximum, but those days in May we are below 70, 64, 52, 50. Okay, so this is an average. So maybe this day in May we're not using the heating system, especially if the average temperature is within the comfort range. So to this day, on Monday the 20th, the comfort temperature, the average temperature is 74. 74, it's fine. It's almost comfort. So that day we shouldn't be using either heating or cooling if the average temperature is like this. Okay, so this day, the average temperature is 71. So there are days in which we shouldn't use any systems, any heating or cooling systems. What happens in June? Okay, in June, the average temperature is 67. The average, okay, so most of days, look at this, the average temperature is 73, 72. Here is 66. Here, the average temperature is 54, 68, 70. Now it's getting higher. Okay, so in June, if the average temperature is very close to comfort and 67.5, 67.5, it's very close to comfort, almost 68. So these days, we shouldn't be using any heating or cooling system because it's close to comfort. And then in July, most likely we would need cooling. Yeah, the average is 76, almost 77. Okay, so let's type here 77. Then August, the average is 71, almost 72. Okay, 72, September. It's 64. October, the average is 53. November, 37. And December, 30. Okay, so now looking at this, and especially looking at this graphic, we have an idea of what we need. Okay, so we are in a cold country, so it makes sense that January and December we need heating, and we are going to need heating in January, February, April, March. Look at May. So if we design the classes wisely, here the heat gains compensate for the heat losses. So here in May, you see that it's negative 700. It's almost balanced. Okay, so in May, just by designing a good um, the designing the openings, we don't need any heating or cooling. In the rest of the months, the summer months, June, July, August, and well, in September, we might need, yeah, so if we design good windows in September, we don't need. So in May and September, we don't need any systems. And here we need cooling, okay, because everything is below zero. So that means that we have negative loads. That means cooling. And then we need to, as of September, as of yeah, October, November, and December, we need a heating system again. Okay, but looking at this, we can understand what we need. And here we have the figures. Okay, so you see that we use 16,175,633 BTUs. 16 million. Okay, so if our clients or if we receive an energy bill, and then the first figure that we notice is 16 million, we say, what? 16 million? This is too much. So that's why if we receive the energy bill, it's not in BTUs. If we have the electricity bill, it comes in kilowatt hours. And if we receive the gas, for example, they don't use BTUs, they use therms. What is a therm? A therm unit of energy is it's this. So one therm is 100,000 British thermal units, BTUs. Okay. And why do they came up with this unit, the therm? Because it's not scary. Okay, so let's transform this into therms. We can say equals this divided by 100,000. And I want only 2 decimal places. Okay, it's 161. It doesn't sound 161. Okay, but if you receive an energy bill 16 million, 16 million, wow, that's terrible. 161, it's fine. This is how human minds work. Anyway, I can include this, and this is the total consumption in therms. And then there's something that you have to remember. One therm, it's around $1. I think it's now the price of the energy depends on the state, it depends on many things, but usually a therm, it's around $1. So if you receive a bill with 161 therms, you will have to pay around $160, $170. Okay, so this is the official British thermal unit, but when you receive a bill, I don't think you have the information in BTUs. You will have the information in therms. And that's it. So in winter, you will pay up to $160, $170. In summer, you can pay $100 for this house. It depends on the size of the house. The bigger the house, the bigger the energy bill. Okay, but with this, at least if you receive 160, it's not as scary as receiving a 16 million, whatever. So for the assignment, we have to copy this. Okay, so we have to insert this table here. And now we have to insert the graphic as well. Okay. So with this information, just by looking at this, we can understand, and we have a color code as well. So here we can understand that the basement is the, well, in winter, yeah, most of our heating loads come from the basement. And the second, it's the ventilation. So what can we do? If we want to reduce this for the ventilation loads, we have to use a heat recovery. Have we used a heat recovery? Yeah. Where is it? Okay, yeah. We have used a heat recovery, 90% efficient heat recovery. So there's nothing we can do. If we didn't use a heat recovery, then the blue value would be the largest one. Okay. So if we look at this, we say, okay, first, let's use a heat recovery. So let's type here 90. It's the average efficiency for a heat recovery. Okay, so now we have reduced this. What else we have to do? The basement. What if we increase the thermal insulation of the basement? Well, I think we have included this R value, the maximum R value. An R value of 12 in the basement is not outstanding. So we can increase the thermal insulation of the basement and we will reduce this. Okay, we can do that. And what's next? The windows. Okay, windows, it's the green, but what kind of windows have we used? Okay, so this is a triple glazing. So imagine that here we are using a double glazing with 0.4. And if we look at this graphic, okay, now the windows are important. Okay, so if we had this, okay, what can I do? I can, if I had this graphic, then I have to show my client these options. Okay, so I want to retrofit my house. What shall I do? Okay, so you can either replace your double glazing for triple glazing, or you can add more insulation to the basement. Hmm. How much does it cost? I mean, what is the cost of these two measures? Okay, if you add the thermal insulation to the basement, this is very cheap, $2,000. But if you want to replace all your windows by triple glazing, you have to spend $6,000. I don't have enough money, so I can start doing this year, and next year I can replace the windows. Okay, we can make decisions, but we can make decisions based on knowledge, because now we have data, we have knowledge, we know what to do. Okay, so this is it. You have to insert this table, you have to insert this graphic, and then you need comments. Okay, so just bullet points. What is this? Or you can, I don't know, maybe you can insert the graphic before and after, and then you can draw conclusions on that about what you have done. Okay, so that would be a good idea, maybe. If you can do this before, without passive house standards, without thermal insulation basement, without the heat recovery, and then you can insert this graphic, and then you can insert the same graphic with improvements, okay, and see what happens. So this is it. But comments are important. So just write 3, 4, 5 sentences about what you have learned by doing this. The second option, or the second thing we have to do is, so this is a yearly heating and cooling load summary. So this is the summary. What about the PV production summary, including heating and cooling demand? Okay, so we have done this with the electric devices. This is what we did last week. But now we are going to include the heating and cooling demand. So the following table, it's this one. What does it mean? Okay, so here you can see that we have the same table, January to December. And what is this row? This is the thermal heating and cooling loads in BTUs. Okay, but now we have to turn this into kilowatt hours because we're going to use electric devices. So when we are talking about electricity, there is not positive or negative, positive for cooling, negative for cooling, negative, no, the other way around, positive for heating, negative for cooling. It's electricity. So I have just include here the same values we had in this table here. But if it's negative, I have just multiplied by -1. Okay, so this is the value, but we have already subtracted the solar heat gains. And if we have solar heat gains, that means that we need electricity to provide a cooling load to get rid of the solar heat gain. Okay, so that's why this is positive. And then we need to turn these units, this is in BTUs, but we need to turn this into electric heating and cooling loads in kilowatt hours. So there is a conversion BTU to kilowatt hour. So this is 1 BTU is 0.000293 kilowatt hours. So if you click here, I have multiplied this times 0.000293. Okay, so I have multiplied this BTU times this, and this is kilowatt hours. Okay, it's positive. By the way, here we have a negative value. So if we have a negative value, that means that we don't have to multiply this times -1, because here everything should be positive. And here we have to type our electric appliances demand. If it was 485, okay, and then we have to drag this. So we assume that every single month we are using the same devices or the same amount of electric energy, of electricity here. Okay, so now we have to add these two things up, because this is the electric heating and cooling demand, and this is the electricity that we need from the appliances. And we should come up with something like this. I mean, if we are working with single family houses in public buildings, in commercial or large buildings, this might be different because electric lighting takes up a lot of energy, because there are huge rooms and we need a lot of electricity to, for the electric lights or the artificial lighting. In single family houses, the graphic should be something like that. So the heating and cooling loads, except in these months, in May or September, usually the heating and cooling loads are much bigger than the electric devices loads. Usually, it depends on what you have done. It depends on the size of the house. It depends on location. But in cold countries, single family houses or small buildings, it should be something like that. If you're working with your design 2 building, this might be different, okay? Because in design 2, the building it's larger than in design 1. So let's see what happens. So just do this and analyze what happens. And now we have to compare this demand, this energy demand, with our energy production, with our PV production. And this comes from PV watts. Okay, so we can go to PV watts. If we are okay, if we are using a DC system size of, I don't know, 9.4 kilowatts, whatever, depending on your roof area, the angle of the panels, We looked at this on Monday, and then we okay, so those are the results. So this is 700, 800, 1000. So here you can type here 700, 850, 1100. This is 1200, and this no, 800. Whatever numbers we can get from the PV watts. Okay. We have this gray line. Excel, it's great because if you click here, you see what row we are analyzing. So this is the electric cooling loads. So these orange values are these. If we click on the blue ones, we know that we are with the electric appliances. And if you click on this gray line, we're analyzing this row. Okay. So here we can see how far we are from the zero energy building. We are far from a zero energy building. Well, in May, it's perfect because we have this demand, and I think the demand and the production are the same. Perfect. In September, well, we are close to the zero energy building. In December and January, we are very far, and even in July, we are far from the zero energy building goal. Okay, so we can copy this. On the second part of this graphic, okay. Let's copy this one. Okay, so this is the first analysis of the current state. And here you can type again the data. Data is, I have used only the roof area, let's say 1000 square feet. This is, let's say 50 panels. Each panel 185 watts. It's times, not divided by. So the total what do you call it in? Yeah, DC system size is 50 times 150, 50 times 9.2. Kilowatts. Okay, so this is the summary. This is your first approach to the zero energy building. You use the roof area of your building. This is the number of panels that you used, and this is the total DC system size, and this is the gray line. It's the PV production. Okay. So we need a plan because this is not a zero energy building at all. And we need a plan for the heating loads, especially for the heating loads. And well, we are not explaining systems here, but I think I have to introduce something about systems because we need to know the options that we have. So that's why I have included this slide to evaluate the PV production. In our hypothesis, we are assuming that our heating and cooling systems are electrical. So we are using electricity to run our heating and cooling systems. Cooling is always electrical, so we don't have any other option. So for cooling, we need to use a device by the name of heat pump. Okay, so we need to use heat pumps. And those are heat pumps. I'm sure that you are familiar with these things or this, or yeah, so we all have seen something like that in our houses. So those are heat pumps. They run on electricity, and this is the air conditioning system. Okay. Then this is the outdoor unit. There are indoor units. So on the walls, we have usually we have this split. Okay. So we have these outdoors and we have these indoors usually. Um, there are different options or different models or whatever, but this is I think we are all familiar with these kind of things. This run on electricity, and this is a heat pump. So for cooling, we have to use this. The good thing is that we can use this for heating as well. Okay, so if we have a system which is an inverter heat pump, okay, so when you have these inverter heat pumps, that means that you can use this for heating and cooling. It's not as simple as this, but we can say that anyway, you can use an electrical heating and electrical cooling system. So there's an option to do that. And this is what we are doing now. Okay, so we are not burning any fuel to heat up our house or our building. For heating, we have different options. Okay, cooling is always electrical, but heating, we can use electricity. So we can use one of those heat pumps, either for heating or cooling, or we can burn fuel. So if we want to burn fuel, then we have to go over the first lesson that we explained back in August. Yeah, the first week, this asynchronous week, when I posted the videos here and I showed you how China was impacting the energy consumption in the world. And here we have, this is not the outcome of the elections. This is just the daily average temperature in the United States. And this is the graphic that we have to remember now. You remember that this is the CO2 emissions of different fuels. Okay, so we have coal, and here I have, well, if we are retrofitting a house and we find a coal boiler, this is the first measure that we have to take. Okay, get rid of the coal boiler and replace this by what? There are two options. We can replace this by a methane or a gas boiler, because in terms of CO2 emissions, it's efficient, but methane, it's not renewable. And methane itself, it's we have to be careful because this is poisonous. Okay, so if we breathe this, we die immediately. The good thing is that we are not breathing this. If it's within the boiler, we are burning this and we are expelling the gases, but we don't breathe directly methane. Okay. Uh, so we have to be careful with this. In terms of CO2 emissions, it's good because we are not emitting CO2 when we're burning this gas. The amount of CO2 that we are emitting is not that much, but this gas itself, it's poisonous. And if there is a leak in our house, we can die. Mm, Nowadays, boilers, they are not, so it's very unlikely that we can breathe this. Even if there's a leak in the boiler, boilers are not in contact with the indoor air. Okay, modern boilers. And usually we have, most of people have replaced these boilers with these kind of boilers that they are not dangerous. Anyway, we have to be careful, and we have to, if the boiler, the methane boiler, it's from the 80s or the 90s, most likely it won't be a safe one. But if it's from the 21st century, it should be a good one, but we have to check it. Okay. Anyway, we have two options. Diesel, well, we have three options. According to this, coal is not an option. Then methane is a good option in terms of CO2 emissions. What about the diesel? Well, I wouldn't do that. So if I found, I wouldn't replace a coal boiler with a diesel boiler. It doesn't make any sense. If I find a diesel boiler, I would try to replace it by one of those because it's more efficient. So I would try to do that. There's another fuel, the biodiesel. It's good because it's renewable. It comes from plants, so you can grow plants. You can burn the oil from those plants, and but it emits CO2. So I wouldn't do that. So, well, some people think that biodiesel it's renewable, so that's a good thing. But I know I'm not very fond of this biodiesel, but there might be different opinions. And another option, so I would think of either methane or gas. This is what we call natural gas or gas, and wood. And now we can burn wood in our fireplace. This is very romantic, very beautiful. But now we don't have wood boilers. We use pellets. Okay, so I'm sure you are familiar with this. So those are pellets. Okay, it's wood, but it's not the wood that we get from the tree. So it's processed so that its combustion uh, capabilities are higher than the actual wood trunk. Okay, but it's wood. So we have these pellets boilers, and it's a good option. What's the problem with this? The problem is the wood life cycle. Yep. Um, what happens? If we plant trees, those trees will absorb part of the CO2 that we emit through the transportation or industry or heating systems, any boilers, we emit CO2, and then part of this CO2 is absorbed by the trees. If we burn wood, we will emit more CO2 to the atmosphere. But the life cycle, the balance is positive. So we can absorb more CO2 than the CO2 that we emit by burning wood. Okay, so that's why when we see this graphic, okay, wood is the worst. It is, yes. But if we consider the CO2 that this wood has absorbed, and now the balance is better. But wood is renewable, so it's a good thing. But we cannot be naive. So it doesn't mean that burning wood, no, it's not harmful at all. It is. The good thing is that if we burn or if we plant as many trees as we burn, the balance would be positive. But just burning wood, it's not an option. We have to burn this, and then we have to replace or replant the trees that we have burnt. That's the idea. Okay. Um, so those are the options. We are not using fuels in this course. We are running on electricity just to simplify things. And that's the other option. We are using solar thermal collectors. Solar thermal collectors are not PV panels. Those are panels, solar panels that produce, that heat up water. Okay, so the solar thermal collectors. Okay, they are, well, they are not the same. So here we don't have PV cells. So, but it's a device, it's another panel. We can put it on the roof, or we can have like an open rack like this. So the same thing that we had with the PV panel. And those are cool. I like these. These are heat pipes. If we look at the TDS center, we have those. We have these kind of tubes or pipes. Okay, probably next week I will explain how these work. But those are, in my opinion, they are more beautiful than the traditional thermal collectors. Well, more beautiful. Well, I don't know. Anyway, we can use this to heat up water. It's very efficient. It's much more efficient than the PV panel. It's much cheaper than the PV panel, and it works perfect. Why don't we use this in New England? Because if you look at the roofs of the houses that you have around the college, um, we don't see this kind of solar thermal collectors because, well, we have to heat up water, and well, it's cold outside, so the water that runs through these pipes can freeze, and if it freezes, it expands and then it collapses, so it explodes. The pipe will explode. If the We can use anti-freezing, you can use additives for the water, but I have talked to some experts, some engineers in New England, and they don't recommend use this. But for example, in Spain, where I come from, using these kind of solar collectors is mandatory. So you can't design a building without using these solar thermal collectors. Why? Because we don't have this freezing issue here, and we have a lot of sun, and this is the cheapest and the most efficient solar technology. It's much better than the PV panels, much better. The PV panels, it's great because it produces electricity, and then we can use this electricity for everything. Here, we only produce hot water, but there are a lot of things we can do with hot water in buildings. We have domestic hot water, the water that we use when we have a shower or we open the faucet or whatever. And we can use hydronic heating systems, like radiators, radiant floors. Okay, so if we are using, let me summarize this. If we are in a mild temperature, it's not too cold. Okay, so if we are, yeah, in the yellowish and red areas of the United States, um, it's a good option. In the blue areas, it's not an option. Okay, but in these areas, it's an option. So I'm sure that there is a market for these kind of panels in the United States, not in New England. Okay, but in Florida, here, California, Texas, all that stuff, we might have a market. Anyway, we're going to use this for domestic hot water. Okay, so next week I will speak about domestic hot water because this is what we have in the TDS center. We have solar thermal collectors for domestic hot water. So at least we will use this. But today we're going to work just with electricity. So we're going to assume that our heating and cooling loads are electric loads. And if we want a zero energy building, we need the right amount of PV panels to produce the same energy that we are consuming. So with the roof area, we will have something like that. We will be far from the zero energy building. What do we have to do now? Well, we need to increase the PV production. And I'm still developing this, and I think we can. Okay, so this is the total electric heating and cooling load. We have to add all these up. Okay, so here we can say that this is the sum of all these rows. Okay, so this is the total yearly energy consumption of heating and cooling loads. Here we have the total energy production from the devices. Okay, so let's wait a minute. Use this color, and here we'll use this color. Okay, and this comes from our PV array. So here we can have the total, and well, we can find this value in the PV watts. Okay, so you have the total energy production here. But if you are doing this, and we can do the same, this is the sum of all these. Okay, so this is the total PV production. So now this should be close to this. We can add this up. This is this plus this. Okay, so this total value should be close to this one. Now this is 9,000, 9,800, and this is 42,000. So we're far from a zero energy building. What do I have to do now? We have to go back to PV watts here. And if our PV array was 9.4 or 9.2 or whatever, and now we have to increase this. So let's try, let's say 40. Go back here. And now this is 50,000. Okay, and we need 42,000. Well, this is not a zero energy building. This is a positive, a net positive energy building. And that's fine, because if we have a good agreement with the company, we can sell that energy, and we can make a good business, but we need to pay a lot of money up front. Okay, so this is something that we have, again, we have to deal with our client, with the electric company, but at least we have this option. So let me I want to copy this. So now the production is 3,100, 3,600, 4,700, 4,770, 537. This is 484. This is 542. This is 524. And 452. This is 344. And 25. And 2. Okay, So now we see here the demand and the production. Mm, the zero energy building, it's about the balance. Okay, so here we need 42 and we have produced 50,000, kind of. So we have a positive balance. So we are beyond the zero energy building goal. That's fine. We are, it's not, it doesn't mean, oh, here I need energy. Yes, you need energy, but we need to look at the balance. So the fact that you need energy in January doesn't mean that it's not a zero energy building. This is a zero energy building. But we do need energy in winter. We need energy in January, February, November, and December. Okay, but the rest of the year, we can sell the excess of energy that we are producing. And okay, now we need to know what do we need, because here we have 50,000 kilowatt hours of yearly production. This is the total yearly production. So this is our second option. So we can copy and paste this option here. I don't want this. There you go. So now we need the data. It's not only the roof area, but the total system size now it was, I think it was 40 kilowatts. Okay, so how many panels do we need now? So 40 kilowatts are 40,000 watts divided by 100 and divided watts divided by 185. So 40,000, 40, 1, 3, divided by 185. So we need 216 panels. Okay, so now there are two questions. The first question is, how much money? The second question is, where? Okay, so you want a zero energy building, the roof area is not enough. So the first, well, this can be the first, or in this the second, or the other way around. Where do we have enough site? Do we have enough place in our site to place 216 panels? And where does it affect the project? Does it affect the landscape? Okay, so we have design conditions here. And then how much? We're not talking about this year, but with our clients, for sure, we have to talk about this. How much money do I have to pay up front? And what is the ROI, meaning return on investment. Okay, so it's a ratio between net profit over a period. Yes, so what is our return on investment? So we pay $10,000 or $20,000 up front. When do we recover this investment, and when do we start making money? I told you that everything that it's above 10 years, it's not a good investment. Okay, so if we make this business and the return on investment is above 10 years, people will not go for this option. And well, it depends on this. It depends on the money that we can make by selling energy to the company. If we don't have a good business here, nobody will do it. Okay, but we're not talking about this. If you want to talk about this, just study a minor in business management. That's a good option. But we are here studying building science, and the building science, it's well, this is the building science. Okay, so how many panels do I need? 260. Great, but this is architecture. To me, the most important thing now is where do we place those panels? And well, this is what we have to understand now. If you are working with a large building and you have a large roof area, especially if you are working with the design two project, maybe the roof area is enough, maybe not. You can let me know here in this first option. If we need more panels in the rest of the buildings, in single family houses, the Wolfson house, the Trubeck house, I don't think the roof area will be enough for the heating and cooling loads. But how far are we from that goal? Okay, so you have to let me know. And then the second option should be what we need to accomplish the zero energy building. Okay, so this is what the building scientist would do. They can, if the client ask a building scientist to, okay, so I want to retrofit my house. Can you please let me know what I do or what are my options or whatever? Um, so the building scientist will come up with this report, with these graphics, which are here, and probably they will include this return on investment. If they are a good building scientist and they have a partner, which is a business manager or whatever, they will include this, and our client will receive this. Okay, or this. So these are your heating loads, your heating and cooling. These are the measures that you can do. You can increase the thermal insulation, the heat recovery, the glass, and then you need to place PV panels. So there are two options. With this, you are far from the zero energy building, but here you get the zero energy building. You can sell these, and you need okay. So you need this. But now we are architects, so we need the where, and even more, we need to convey this information. Okay, so this is a way to convey the information, and this is what engineers, building scientists would do. We are architects. We need to go further. So this is the second part of the assignment. Yeah, so we need to convey these sustainable design strategies. Okay, so we have already done this. We have calculated, we have analyzed, that's good. But for architects, it's not enough. We need to convey this information in a graphic, in a nice drawing. So that's why I have shown you, I have uploaded some examples here about architectural design strategies. So you have different drawings, and well, this is what is written in the statement. Using a section view or a 3D view of the building. A section view would be enough. If you are designing a building, for sure you will have to show section views for your design project. If you are analyzing one of the Louis Kahn house, you have to take a section or a picture or a 3D picture of the building, and then you have to try to do something like that. I can help you, so, but I want you to try first, and then I will help you do this. Okay, so we need information like that. And you can do it, okay, because if you have a perspective like this with your roof, so here you have this information. So you know the size, the DC size of your PV array, of your photovoltaic system. It's 63.5 kilowatts. Okay, uh, you can type this. Do you have a continuous installation? Yes, you have. You have the R value of this is R45, by the way. So we are better at this because our R values are above R50. Okay, so you have these numbers, and this is a nice way to convey all this information. It's not just showing graphics or tables. This is more architectural, and at the same time, you are talking about the design of your house, and you are talking about these energy values. So this is what I want you to do. There are, you can go over this, you can read this. There might be some things you don't understand because it's related to systems. We haven't talked about systems, but we have talked about airflow. You can use heat recoveries somewhere. We have talked about insulation, and we have talked about PV panels. Okay, so at least these three options, you have to include these three: the thermal insulation. You can talk about the glass as well, the thermal insulation, the glass, the ventilation, and the PV panels. You can talk about this. And then, well, I have shown you different examples. The orientation of the house is important as well. So here you have different examples of sections. You can use a hand drawing like this. It's nice. Okay. So with this hand drawing, you can include here the PV panels, clerestory windows. We have not talked about these natural ventilation strategies. This is more for warm climates. Well, but you can include greenhouses. I don't know if we have a greenhouse example here. No, we don't. Okay, but you can talk about the different angles of the sun. So here we have the summer sun, here we have the winter sun. Here we have another photovoltaic array with 23 kilowatts. Okay, so try to produce something like this, a drawing. By Monday, I would like to see something like that. You have time to improve it, so you have 2 weeks to do this. And I think it would be great if one of your drawings for your final design presentation, it's something like that. It's something including the thermal analysis that you have on your house for your design project. Anyway, this is what I expect from you. I expect the first version. I think hand drawing would be good for this first attempt to convey this information. Okay. But I want to show you this architectural. Well, we have this bioclimatic design, sustainable design. All these words are, I think they are exhaustive. Okay, so when I was a student, nobody told me anything about this. So design in architecture schools was about different things back in the 80s or 90s. Getting old. But it changed in 21st century. There was another recession, probably because it was after the second Gulf War. So there was another issue about energy. Energy became another issue in the world, like 20 years ago. And now it's still an issue. And then all this movement about global warming. So there was another concern. So now we are in the middle of nowhere, but energy is important, global warming is important, reducing CO2 emissions is important. So we have to include this in our design strategies, okay? The word bioclimatic, it was in fashion like in the, I don't know, 20 years ago, but everything was bio 20 years ago. So people stopped believing in bio things. Everything was bio. Even if there was a biodiesel and biofuel and bio whatever coal, everything was bio. And then we had the sustainable. Everything was sustainable. Sustainable whatever, sustainable transportation, sustainable whatever. But we have to go beyond the words, and we have to do things that are meaningful. And what are meaningful strategies? This is what I want to show you today. We are talking about passive heating and cooling strategies. Let's talk about passive. Active strategies. PV panels are active strategies because they are producing energy. Even heat recovery, it's an active strategy because we can turn it on and off. A passive thing is something that we can't change. We can't change the amount of thermal insulation that we have in our building. So this is a passive strategy. We can't change the glass of our windows. Well, we can, but we cannot change it today and tomorrow. No, we have to make that decision, and we are designing this house with a triple glazing, and that's it. We can't change the slope of the roof. No. We can't change the fireplace. No, if there's a fireplace, we can't change it. Okay, so those are passive strategies. For heating, and we are working in New England, all your projects are placed in New England, so you have to apply these heating strategies, the cooling strategies. I don't think that you can work with them in this exercise, but anyway, I will explain it as well. We know this. We have solar heat gains, and we can work with the glass selection. We know that we have the U value of the glass, the solar heat gain coefficient, so you can talk about this. We have thermal insulation, is related to the R value, to the passive house standards. And we have a central fireplace. I think I've already explained that, especially in Frank Lloyd Wright's buildings. Okay, these Usonian houses that Frank Lloyd Wright designed in the 50s, or yeah, I think it was in the 40s or the 50s. They are simple houses, and I think I have already explained you this. They have a large window area facing south, and they have small openings facing north. So let me, if I can find the north elevation. Well, yeah, this can be a north elevation with small openings, as you can see, and the south elevation is just the other way around. But if we look at the plan, okay, so we can see that there is always a thick wall with a fireplace just in the, this is the fireplace in the middle of the living room. Okay, so there are different versions of these houses. No, this is not a Michelin house. Okay, there is always a fireplace. We have big openings facing south, small openings facing north. Okay, so there is always a fireplace here in the middle of the house between the living room and the bedrooms, and openings, big openings to the south, small openings to the north. Okay, so this is the key to success, and we are not better than Frank Lloyd Wright. So if he was doing this, okay, this Zimmerman house, it's interesting. Because it's in New Hampshire. Okay, so this is in Manchester, New Hampshire, and well, it has all the features of Frank Lloyd Wright's house. South elevation, north elevation, and overhangs to protect the south elevation from the wind, from the summer solar sun. Okay, so that's it. And the fireplace here in the middle of the house. Okay, so we have a brick wall with a fireplace, so that we heat up the fireplace during the day, and then during the night it releases that heat that yeah, that we have within that wall. No, this is not. A very it's an outstanding building. It's you can visit this. Well, you can. I don't know now, but last year I visited this building and it was outstanding. Very simple, but it catches the eye. So it's something special. You can understand that you are looking at something special when you are at this house, and it's not. I mean, why don't we copy these kind of houses instead of? I don't know. Anyway, my favorite Frank Lloyd Wright's house. It's the solar cycle. Yeah, this one. Okay, it's the same concept. This is facing south, a huge wall, glass wall here, and looking north, it's like this. So it's buried. Okay, so it's not a thick wall with with small openings. It's just that it's like a hill, and the house is like carved on that hill. So I think it's a great idea. And yeah, so this is it. So this is the south side, and this is the north side. Okay, so it's almost underground. This north side. Uh, Beautiful and very simple. I mean, it's not a concept. Okay, no, he's a genius. I cannot do that. Yes, we can. It's pretty easy. It's a good idea. And it works. And if we look at the plan, okay, so we also have the idea of the fireplace here in the middle of, yeah, in the middle of the living room. We have a fireplace so that we can make the most of heating up this thick wall here. And look at this, look at the space. It's an open space, and upstairs we have a couple of bedrooms, and that's all. So, but we don't have anything, any partitions, we don't have any columns. It's an open space. It's an open space except for the bathroom, for sure. It's not open. Okay, so the central fireplace and all that stuff. Then we have greenhouses and trombi walls. So those are things I'm sure that you know what the greenhouse is. Uh, and the trombi wall, well, I explained this. Greenhouses work well in cold countries because we have an area that is made of glass, and it can make the most of the winter sun. So this is what a greenhouse is. For sure, it has to be south oriented. If we have a greenhouse oriented to the north, it's a huge mistake. But greenhouses, um, they are beautiful. People love it. Why? Because you have a lot of glass area, and when it's cold outside, and you know that it's cold outside in a winter sunny day, being inside this place without any heating system, you don't need any heating system because you have enough sun. Uh, it's a wonderful feeling. Okay, so people appreciate that, and yeah, it's a nice idea, and we don't need to. It's just using glass and wood, stone, materials that people like, and plants. That's it. This is people are happy just living in a place like this. So let's do it. There's a physics behind it, sure. So we need to understand that, yeah, we need a glass here, and we need to compensate the solar gains with the heat losses. Mm, for sure, we have to use a glass here with a very high solar heat gain coefficient. The U value is not as important as the solar heat gain coefficient. So sometimes we don't have to use even a triple glazing here, because most likely this is not a heated space. Okay, so we use this space if it's a sunny day outside, we can live here without any heating systems. But if it's snowing and we don't have any sun, we just don't live here. So that's why we have the wall, and this is the wall with thermal insulation. Okay, so we don't have even thermal insulation on the roof. We don't need it. Okay, because we are not using this place if the weather is not fine. I mean, if it's cold and without any sun, we are not using it. If you want to use it, probably you will need to place thermal insulation here. You will need to use triple glazing, but then the physics will be different. Okay, but just by using this, an area that it works when it's sunny outside, and it doesn't work when you don't have any sun, well, that's fine, because the thermal insulation is here. There's a limit between the greenhouse and the Trombe wall. Okay, so here, what do we have? We have a glass attached to this wall here. We have a thick wall made of brick, this one, and we have this gallery. A greenhouse is a place in which you can stay and you can place a table and 4 chairs, and you can have a breakfast or a lunch here. This is a gallery. Do we have enough space here just to walk? Well, I don't know. With a Trombe wall, we don't have any space here. Okay, a Trombe wall, it's a wall, a thick wall, and we have attached glass here. Where does this word come from? Well, it's named after Felix Trombe. We don't have pictures. Okay. Anyway, he was a French engineer, and he designed this. We are talking about 1950. Okay, so it's not something new. But this is the idea. Okay, so we have to do this in the south elevation, and we have a wall, and then we attach glass. But it's not a gallery. People cannot stay here. I'm not very fond of this solution. It works. I think there are better solutions, or I think we can combine different solutions here. And well, I have some friends that they build a Trombe wall. Yeah, I think they were designing that building, and they use these Trombe walls. Okay. You can use it, but we have to understand what we are doing. So we need a wall, and we need this glass attached to the wall, and then we have this air chamber. Of course, if it's south oriented and there's plenty of sun, the sun heats up this air, and I mean, it works because it's natural. We don't need to force the air. So the cold air will go down naturally. Then we have this ventilation, this opening, this small opening. So the cold air will go through this ventilation. It will heat up here. So the hot air tends to go up, and then it goes inside again through this upper ventilation opening. It works. It's easy. And all you need is a wall, bottom openings and upper openings, and this is the air movement. It's natural, so you don't have to force this air movement. There's a debate whether we should add thermal insulation or not to this wall. This is a good question because, well, um, if you want this wall, uh, imagine that we don't have any sun. Okay, we don't have any sun. We close this opening with something, with a door that has a thermal insulation on it, and it works as a wall. So if we don't have any sun, no, there's no problem. The problem is that if we do have sun, this wall will be heated up, and then during the night it will release this heat through the inside. So if we place thermal insulation here, this heat is not released inwards, it's released outwards because we have thermal insulation. So there's a debate. I don't know, it depends on the size of the Trombi wall, it depends on the place, it depends on how many hours of sun we have in winter. It's not an easy answer, and it depends on many factors. Anyway, you can use this, but I don't know. I like this. I think it's cool. It's not a glass house because it's like a gallery. Yeah, you can call it a gallery, but I don't like the Trombi wall. Anyway, you can use it or it's an option. And then we have, this is for heating strategies, passive heating strategies. We have cooling strategies. So in cooling strategies, what do we need? We need shade. So we need shading devices, overhangs, louvers, whatever. We can't, now sun is the enemy because we have a lot of solar radiation and it's hot outside. So we need to prevent the sun from entering the building. We can use thermal insulation for sure, but we have to add thermal mass. So we need heavy roofs, heavy walls, because with heavy elements, using brick, stone, concrete, wood is not heavy. Wood is good for cold countries, but it's not as good for hot countries. Okay, brick, concrete, stone, natural stone, those are heavy materials, and they can accumulate a lot of energy, a lot of thermal energy, so that this thick wall can be heated up during the day, and then during the night it will release that energy outwards, not inwards. Okay, so we need thick, heavy materials for walls and roofs. Green roofs are good options for passive cooling strategies because they add thermal mass to the roof. And then we need the strategies, night ventilation and basements, underground rooms, basements. Okay, so I can show you a couple of examples. I like this. This is in Africa because they show us that with no resources and no technology, they can achieve comfort and with good architecture. So what do they have? They have this umbrella for the shade, and this is a shaded area, and they are fine here because they are not under the sun. Okay, so we have this area and we have shade. This is what we need here. The buildings, look at this, the walls are made of brick. This is brick, and they are pretty thick. And they are narrow. Those buildings, you can see that they are narrow. Why? Because they need the ventilation, so they need airflow. Because by being exposed to an airflow, you feel, you cool down, your body cools down. Okay, so the buildings are narrow. They have openings in two directions, in two orientations, so that the airflow can go through the building. If the building were wider, the air wouldn't go from this point to that point. So that's why we need a narrow building to do that. If you look at this, it's the same option. We have this roof to provide shade. People are in the shade, they are not in the sun, so they are. We have narrow buildings with openings both sides, and that's it. So that works. And heavy walls made of brick. So with these passive strategies, they achieve comfort without technology. I don't mean that we don't have to use technology. Of course we have to, but we don't have to rely on technology. First, we need to work with passive strategies, and then we can apply the technology. And these are schematic drawings of this. We have basements, and why do we have basements? Because the temperature of the soil is lower than the air temperature. So when the weather is too hot outside, being in a basement under grade, it works. And the temperature down there is a challenge because we need to provide this basement with natural light. Okay, so that's another challenge. But basements work in this kind of hot climates. Water, you have to collect rainwater because it doesn't rain a lot, and you need to collect rainwater. But you can use pools or water ponds, whatever, to cool down the air. Because by having water, you cool down the air. And well, you can use green roofs. Everybody like it. It's cool. It's beautiful. And then there's this kind of architecture. Is this a green roof or I know it's the architecture is carved in the soil here. Okay, so it's a good strategy. It's a good design. So buildings are. It's not a green roof because this is just the well, this is the soil. So the architecture is carved there. And it doesn't mean that if we are applying these kind of strategies, we can combine PV panels on a green roof. So we can do both. Okay, so and I think we have to learn from countries in which they don't have technology, they don't have heat pumps, they don't have technology, and they are in comfort even in a warm country. And we have to learn from history of architecture. So I can show you my favorite place on earth. Okay, so this is Granada, Spanish city. And what do we have? It's quite hot here. So it's the south of Spain. So we are above 100 Fahrenheit many days. And what do they have? They have shade, they have thick walls, and they have ponds. And fountains. And that's it. It's very simple, very humble, no technology, but it works. You are within those buildings and you feel like life is wonderful just by using local materials, brick, gypsum, local plants. So it's nothing. I mean, there is no technology. It's not you don't use the titanium for the facades, but it works and it's beautiful. So we have to learn from this local architecture because yeah, and by using fountains, plants, you cool down the air by using these kind of strategies.